Okay, so since it's been so long since the previous talk, I think it's a good idea to recap what we were discussing last year. So we have this reductive group over Q. We have arithmetic group. We have the group of real points, which is a Lie group, maximal compact subgroup, the split component, and then the global symmetric space, and the locally symmetric space. And we have our representation giving us our coefficients, and we can do the cohomology of gamma with coefficients in the Z gamma module E by looking at the cohomology of the quotient with coefficients in this associated local system. Okay, so I want to talk about some further properties of cohomology, and there'll be definitely be some overlap with what Luke was saying today, but maybe it doesn't hurt to see it again. So again, let's look at SL2 over Q with this standard congruent subgroup, Hecke congruent subgroup. And we know that H upper 1 is isomorphic to a sum of the Cusp forms and their conjugates in the Eisenstein series. And for SL2 over Q, H upper 1, this is the only interesting cohomology group. What is this thing topologically? Topologically, it's just an orientable surface, but it's punctured. It's missing some points. And when you know from algebraic topology class is that if you take a surface and you puncture it, it deformation retracts onto a graph. So it's, in terms of its homology, cohomology, it can only have something happening in degrees 0 and 1. And of course, degree 0 is probably not the most interesting cohomology or homology group to look at. So that's really H upper 1 is the only game in town for SL2 over Q. And that's why people have gotten so much mileage out of it. So also we see that, as I said last time, the cohomology is computed in terms of automorphic forms, and there are sort of two types of forms appearing here that are conceptually very different. We have the Cusp forms, and we have this complement, the space of Eisenstein series. And so there are various ways to say that what the difference is. The Cusp forms are the things that have very rapid decay as you go to infinity, the modular curve. And the Eisenstein series, on the other hand, they're still modular forms, they're holomorphic in infinity, but they don't have that rapid decay. And from arithmetic applications, the Cusp forms are much more interesting. The Cusp forms are the ones that, sort of the mysterious part of the cohomology. The Eisenstein series part, it's not that it's totally uninteresting, it's certainly not. It's just that it's, from an arithmetic point of view, we understand it so much better than we do the Cusp forms. Okay, but this is the picture for SL2 over Q. So now what happens in general for a general arithmetic group? Okay, so we talk about the virtual cohomological dimension. And again, you're going to hear about this again, definitely more than once. So, but let's look at from different points of view. So suppose Y gamma has dimension D. So because it's a topological space, it's basically a manifold. It's an orbifold, but it's close to a manifold. We could have non-zero cohomology in these degrees, 0 up to D. Okay, but in fact, that doesn't always happen. So we're going to define the Q rank to be the dimension of Q split maximal torus in G. So for SLN, for example, the biggest torus you can have is going to be Q cross to Q split torus is going to be Q cross to n-1. So the Q rank in that case is going to be n-1. For SL2, it's 1 and so on. So the cohomological dimension of a group we define to be the least n, such that when you get above that n, you always get vanishing in the cohomology for all possible modules that you consider. Okay, if the group has torsion-free subgroups of finite index, then it turns out, there's a theorem, that the cohomological dimension of all of them is the same, and that we call the virtual cohomological dimension. So in general, if you have a property of a group, you talk about having that property virtually if you have it for the torsion-free subgroup of finite index, okay? And lots of properties are stated that way. So the VCD is what the virtual cohomological dimension, that's what we call it here. So as the theorem of Borel and Serre, which will be again discussed by Peter and Jenny, definitely, is that there's actually a computation of the VCD for any arithmetic group. It's a remarkable result. It says that the VCD is the dimension of the symmetric space minus the Q rank of G divided by its radical. So if G were semi-simple, the radical would not be there and it would just be the Q rank of G. But because we allow reductive, we have to put this in, okay? So remember that reductive was basically semi-simple times central torus. And so this is just saying that central torus is not contributing to this, to this discussion. We only care about the associated semi-simple group, okay? So here's an example, which, I hopefully computed this correctly. I know I'll get a violent objection if I didn't, so that's good. But the dimension for the symmetric space is that, and then, oh, I already made a mistake, didn't I? So it's that -1, okay, sorry. And then the rank is n -1, and VCD is that. So there is a mistake there. So in before violent objection. Okay. Okay, now the cohomology is built from automorphic forms, and this was discussed by Haluk today. There's a certain collection subspace of this coming from the cusp forms. It's called the Cuspidal cohomology, okay? And the Cuspidal range is the set of cohomological degrees in which this can appear. So this is clearly, by almost any stretch, the most interesting part of the cohomology, the most mysterious part of the cohomology. And typically it's a very small piece of the cohomology. And where does it live? It sits on an interval centered on half the dimension of the symmetric space. And the length of that is called delta of G, the deficiency of G, okay? And typically it's very small. So why is it called deficiency? Because after all, if we say this is the most important, interesting part of the cohomology, we want delta of G to be big, right? Because wouldn't that mean that it's a lot of it? It sits in a lot of cohomological degrees. So why is that deficient to have a lot of degrees where cusp cohomology can appear? Well, it's because deficiency is referring to something else. So it turns out it's that as Haluk called it, the fundamental rank, the deficiency is 0 if and only if this associated Lie group G has discrete series representations. So having discrete series representations is very important and very useful. And if you don't have them, you're certainly deficient. So if how big this number is sort of saying how far away you are from having discrete series representations. So from that point of view, it's certainly something that is deficient, bad.
Can you say again, Paul, can you say again, what's the discrete series representation?
Discrete series representation, so it means it occurs discretely. So for example, well, I guess I don't want to try to give a definition that's going to end up being nonsense. So, but I don't think I want to say more than that. I mean, I'm not an expert on representation theory of real groups, so I don't really want to say something silly. But it's true for SL2 over R, but not true for SL3 over R. Okay. Sorry, that's not a very useful answer, but in any case, from the point of view of that representation theory, this is very good to have for various reasons. And if you don't have it, it's bad. So, but one person's trash is another person's treasure. So we like to have this number. We would like to have this number be as large as possible if we want to compute cusp cohomology. Here's an example of just a table for how it varies for SL and Z. So the top row shows the dimension of the symmetric space. And the next line shows the VCD. So the Q rank of SL and Z, of SLN over Q is n-1. So that's why you have this gap between the VCD of gamma and the dimension. And then the deficiency it's growing linearly as you go up. And as Haluk mentioned, this is, I mean, I actually highly recommend the same survey paper that he was talking about by Schwärmer and Lee. It gives you sort of, this also appears for SLNZ in an earlier work of Schwärmer, but in any case, there's the computation of it. So for SL2, we have deficiency is 0, and so the cusp cohomology sits in 1 degree, and in that case, it's an interval of length 1 around the middle of the dimension of the symmetric space, so that's just in degree 1. Just in degree 1. For the next case, the deficiency is equal to 1. So the interval has length 1, and the half of the dimension of the symmetric space is 5/2, 2.5. So it has to be an interval of length 1 sitting around 2.5. So there it is. It goes between 2 and 3. And as you can see, as you go to the right, this deficiency is growing. It's growing linearly, whereas the dimension of the symmetric space is growing quadratically. So as you go further and further to the right, the cohomology becomes sort of further and further away from the top degree, the VCD. It gets sort of deeper and deeper into the space. And from a computational point of view, it makes it much more difficult to get your hands on, okay? That's why, so for SL2Z, H upper 1 is sort of the only interesting group. That's exactly where the cusp forms appear. It's also the VCD, and we have the most technology for doing computations with that. When you get above that, it starts to become more difficult, but already for SL3Z, at least the top degree where the cuspidal cohomology appears is the same as the VCD. So we can use a lot of the same kinds of things that we do for SL2 for SL3, but things have to change as you go further down the list. It becomes more complicated. Okay. Here's an example, sort of to complement what Haluk was talking about, for SLN of O of F, where F is imaginary quadratic. So in this case, symmetric space is SLNC over SUN. And again, you see the dimension is growing quadratically. In fact, it's not that hard to guess a formula for what the dimension is from the table. And then the VCD is, well, there you see it. Again, the Q rank is n-1, okay? Q rank is n-1. And this time, the deficiency is just growing linearly by 1 at each step. The top degree, you can see there, and the bottom degree. And again, for SL2, the top degree of the cuspidal range coincides with the VCD. And so the same kinds of tricks that we use for SL2 over Z, we can use to compute there. And there are other ways to do it as well, but in any case, that's one way to do it. On the other hand, for SL3, we have to do other things. If you wanted to go even further up for N, we'd have to do even more different things. Okay. In the case where the Q rank is positive, the symmetric space, locally symmetric space is not compact. That's if and only if. So we see that in the cohomology. In fact, if we compactify, so the open modular curve Y naught of N, there's a standard way to make it into a compact curve, and that's just by adjoining the so-called cusps and just filling the punctures with points. If you do that, then what happens is that the cohomology is now different. Okay, so first of all, it's now a compact surface, so you actually do have H upper 2. It's a compact orientable surface, so you don't really learn anything from H upper 2 that you don't know from H upper 0. But in any case, H upper 1 now changes. So there was some part of the cohomology that was associated to those punctures and has now disappeared. And when you compactify, you don't see the Eisenstein part anymore. You just see the cuspidal part, okay? So what that means is, if our space is not compact, we might be able to profitably understand something about the cohomology by compactifying it, looking at the cohomology of the compactification. And so I want to talk about this. This will also be talked about by Peter tomorrow, but maybe this will be a slightly different picture on it. The point is that in general, when you want to compactify a locally symmetric space, that's quite a complicated thing to do. The geometry of these spaces is way more complicated than what you might expect from just the only example that you know is the modular curve. In a topological surface where you've drilled out some points is not that easy to imagine various ways to compactify it. But for a general space, you know, we don't want some silly compactification like the 1-point compactification, which you can do for basically anything. We want some kind of compactification that's going to reflect the structure of the space and somehow tell us some structure about the cohomology. Okay.
Paul?
Yep.
Quick question. So this is only about SL2Z, right?
The thing I wrote there?
Yeah.
Yeah.
Okay. And or are you talking about other compactifications right now too for different groups?
Yeah. I mean, I said, like, I'm just saying, right. So for SL2, for SL2Z, SL2Q, when you want to compactify, the space that you have is just a topological surface minus some points.
Yeah.
And compactifying that, you know, it's not hard to imagine how to do that. In fact, even how to imagine various ways to do that. But for these higher dimensional spaces, you know, sort of the only compactification anybody knows in general is the 1-point compactification, which is not very exciting. But we want to compactify it in some way that reflects the internal structure of the space and is going to be useful for cohomology computations. That's all I'm saying.
Okay.
I don't know. I guess I'm kind of talking about two things at once, but in fact, so this last part of the slide here, so there are various ways to do this. There are lots of different ways, and I'm going to talk about some of them. And in fact, the way to do this usually is not to compactify a given d divided by gamma, a given y gamma. Instead, what you do is you partially compactify the global symmetric space. You put some stuff at infinity, you enlarge the global symmetric space by adjoining some things to that. And then you do that in sort of a nice way with respect to the gamma action, and then you mod out by gamma and obtain a compactification of y gamma. And the virtue of doing that is that you sort of treat all examples at once instead of sort of doing them case by case for various gamma. You want to somehow do everything gamma equivariantly on D, and then you get something for all gamma. And this is something that you've already seen when you think about compactifying the modular curve. We don't take the curve y naught of n and then just say add some points to make x naught of n. What we do is we take the upper half plane, which is the symmetric space D, and then we add the cusps at the rational points at infinity in the upper half plane. We add the rational points in the real axis, and we add the point at infinitely far up the imaginary axis. So that's not a compactification of the upper half plane, but it's like a partial compactification. We sort of thrown some points in. And then when we mod out by gamma, if we put the right topology on the upper half plane union with those points, we get something reasonable. Okay. All right, so now there is a lot of different ways to compactify a locally symmetric space. And so I'm going to go through them. So and I'm not going to give, I'm really not going to say much of anything except you're at a family reunion for someone's family you don't know, and they're pointing at the various relatives and saying, this person did jail time, this person is president of the US and also did jail time, and so on. I'm going to tell you names, but the point is that you can now go and hope. The literature on this subject is pretty opaque. It's pretty difficult to sort of get into it because it's so technical. But I think if you have some pictures and names in mind, it will help you understand in general how to approach it. At least it certainly helped me when I was a student. But anyway, let me just go through some of this. So first of all, there's the Borel-Serre compactification. So this compactifies a locally symmetric space to what's called a manifold with corners. So topologically, that's just a manifold with a boundary, which you're familiar with from algebraic topology class or differential topology class. But it has a sort of a refined structure. So locally, it doesn't just look like an upper half space like Rn, where you make one coordinate bigger than or equal to 0, but it looks like locally like orthants in Euclidean space, like where you take, for example, r to the n and multiply it by r bigger than or equal to 0 to the m. Okay, imagine doing something like that. So think about in 2 dimensions, it would be something that locally looks like 2-dimensional Euclidean space, or the upper half space, or the corner, the positive quadrant in R2. Okay, topologically just a manifold with boundary. But the construction of this space is the key part of what's called the Borel-Serre vanishing theorem, and also Borel-Serre duality that will be discussed tomorrow. Okay, so that's a nice space. It's a manifold with boundary, which we know is a nice thing. But in some sense, it's actually, in some ways of looking at it, it's not that great. So it's sort of too much for some applications. So there's a variation on this called the reductive Borel-Serre, which is obtained from the Borel-Serre by quotienting out some things. And I'll give you an example in a moment. But the point is that it's not a manifold anymore after you do that, not a manifold with boundary. So we don't do anything in the interior. We don't change y gamma, but we do change what's happening at infinity by squashing some stuff away. So from a topological point of view, that's not so great if you don't like spaces like that. It's a singular space. It's not a manifold. So it's more complicated topologically, but actually from a differential geometric point of view, it's better. So one drawback to the Borel-Serre is that, as we talked about in the last lecture, there's a natural metric on the global symmetric space. And when you take a quotient by a discrete group, you get a metric on that space. The metric is invariant on the global symmetric space. So when you take the quotient by gamma, you get a metric on the quotient. And this is definitely something you should be familiar, like take a hyperbolic plane. It has a metric on it that's invariant under SL2R, in fact. And so when you take quotients by subgroups of SL2Z, you get a metric on those. So they're not just topological surfaces, they actually have a nice metric on them. And in the Borel-Serre compactification, when you take this nice metric on the interior and you go to the boundary, it becomes degenerate. There's sort of large sets at infinity where that metric is degenerate. Okay, so that's not so great if you're trying to do differential geometry. So, but the reductive Borel-Serre rectifies that problem. The reductive Borel-Serre, the metric on the interior does extend to a non-degenerate metric on the boundary. Okay, so that's, okay, you're exchanging one thing for another. That it's worse topologically because it's singular, but metrically, at least you have a non-degenerate metric, which some people are very happy about. Okay, so those are for reductive groups, in particular semi-simple. When G is semi-simple, you have another collection of compactifications called the Satake compactifications. So there's a finite list of them for any example. They depend on the choice of a weight. And what you get usually get different compactifications for different weights, okay? So imagine a whole tower of them where you've chosen a weight. In fact, it works. So how does the weight come into play? Well, the weight gives you a way to embed the global symmetric space inside of a cone, and you end up taking a closure there. So the weight changes the embedding and changes what happens at infinity. And you get a whole tower of them. So the top one is very often the same as the reductive Borel-Serre. So that is the case, for example, for the symplectic group or SLN. The top one is the same as the reductive Borel-Serre over Q. But the smallest ones, as you go down the tower, as you change the weight that's determining the compactification, you get pretty bad singularities. And at the very bottom of all these compactifications, you get something that's quite singular, like very difficult in some sense to understand the geometry of its singularities. If you have a Hermitian symmetric space, like for the symplectic group or SO2N, then you have what's called the Bailey-Borel compactification. Okay, so in that case, we said the locally symmetric space is the locally symmetric space actually has the structure of a quasi-projective variety. So there's a way to turn it into a projective variety by taking a closure. In fact, you take the graded ring of automorphic forms on the space, and that gives you a place to take a closure. You get a projective space there, and you take a closure. So, but it's nice in that it's canonical and it's an algebraic variety, but it is incredibly singular. It's very difficult to understand its topology and its geometry. And to give you an idea of how singular the Satake guys can be, one of the minimal Satakes, might regard as being a non-Hermitian analog of this. So in the case where they are the same, like a Hermitian case where you have both notions, it is the same thing. So it gives an analog of that in the non-Hermitian case. But the singularities are very complicated. It's very difficult to work with. And finally, because in algebraic geometry, if you have something singular, you want to resolve the singularities. That's one approach to dealing with them. There's a way to do that, and that's called the toroidal compactifications. So they give an explicit resolution of the singularities of the Bailey-Borel, but they do have the drawback that usually they're not canonical. So they depend on a choice of polyhedral decomposition. And one of the underlying themes of this summer school is polyhedral decomposition. So Voronoi's work in polyhedral decompositions of the space of quadratic forms is extremely important here. And in fact, is one of the main engines that behind the construction of these toroidal compactifications. But we're not going to say much more about them just because it takes us a bit afar from what we're doing. But they're very interesting, extremely interesting, and definitely worth taking a look at if you haven't seen them before and you're interested in this kind of thing. So now I want to give some examples. And again, tomorrow you're going to actually hear more about this example SL2Z from Peter, but I'll just say a little bit about it. So in this case, the quotient y gamma is a punctured topological surface. So how can you compactify that? Well, one way would be to fill the punctures with circles and make a manifold with boundary out of it. Okay, and that's sort of a perfectly reasonable way to do a compactification. That's not what we're used to if we study modular curves, because we don't get an algebraic variety anymore. But in any case, that is a way to do it. The reductive Borel-Serre, in this case, is the same as the unique Satake compactification. And in fact, in this case, is the same as the Bailey-Borel. And that's where you take those punctures and you fill them with single points, which we call cusps. Why do we call them cusps? Well, because metrically, it looks like you have a cusp at that point. It doesn't look like a nice, the picture of a single point sitting inside of on top of a sphere. It doesn't look like that. It looks like a very sharp point metrically. And this already shows you the difference between the reductive Borel-Serre and the Borel-Serre. So the Borel-Serre, if you go to infinity up the upper half plane, and you have sort of two parallel lines going up, then the distance between them becomes 0 in the limit. Those points going along two parallel lines parallel to the y-axis in the upper half plane, as you go infinitely far up, become metrically arbitrarily close together. So if you glue in a circle there, you're not going to be able to distinguish the points on that circle metrically, because the metric has degenerated there. But if you fill it in with a single point, then that is what makes sense metrically. And in this case, that's the only, this thing actually ends up being topologically a manifold, so that it's not singular. So we don't have this problem that we have in general with the Bailey-Borel or Satake compactification. We already see something different and something new in the real quadratic case. So in this case, the locally symmetric space is the Hilbert modular variety. In fact, it's called a Hilbert modular surface. It's an algebraic surface. As a real space, it's 4-dimensional, and it's an orbifold. It has some singularities inside coming from torsion in the group gamma. Okay. When we construct the Borel-Serre, so it's 4-dimensional, so we're going to make a manifold with corners or manifold with boundary. You have to glue in something 3-dimensional. The things that get glued in this case are boundary components that end up being torus bundles. And here, these are the actual true tori that you buy in the donut shop over S1. So they're fiber bundles over a circle where the fiber is a torus, okay? In the reductive Borel-Serre, what happens is those tori in the fibers get squashed away. They get collapsed down. So the boundary components in that case are just circles, okay? So of course that can't be a manifold with boundary now, because you've taken a circle and you've glued it on, which is 1-dimensional, and glued it on at infinity to something 4-dimensional. So it's not possible to have a manifold with boundary anymore. But the metric does extend non-degenerately to those circles. And in fact, the only thing that was going wrong with the metric extending was what was happening in those tori. Finally, in the Satake Bailey-Borel, because again, this is an algebraic variety. So there's one Satake compactification, and it's the same as the Bailey-Borel. those S1s get collapsed to points. And now it's quite singular. You have a 4-dimensional thing, and at infinity, you've glued in a 0-dimensional thing. So you're pretty far away from being a manifold at this point. And in this case, resolving the singularities was originally done by Hirzebruch. And this canonical toroidal resolution in this case. See, sort of the surface is the only case where there's a canonical Hilbert modular case where there's a canonical resolution. And it was the sort of, this resolution is what started the whole industry of constructing toroidal compactifications in general by Mumford and his co-authors. And it also is what started toric varieties. So this is really so again, this is emphasizing what I said in the first slide of the talk of the whole series, is that for all these spaces, they're so important because they're connected to so many different things. They're not just sort of like, they're not those crazy spaces you learn about in topology class that no one cares about. They're spaces that are related to everything somehow. Very interesting. So I can't really talk about how these work, and it's just too complicated, but I do want to give an idea of the general scheme of how they're made. And I'm going to do SLNQ. So there'll be some overlap with what you hear from Peter. But so first of all, recall these proper parabolic subgroups, the block upper triangular subgroups and their conjugates. And we're considering only the proper ones. So we only want the block diagonal ones where we have at least 2 blocks on the diagonal. Okay, so those are some nice subgroups of GLN, SLN. And first, what we do is, so I said the strategy for constructing compactification was not to treat the locally symmetric spaces one at a time, but instead you start with the global thing, and then you partially compactify that. So first what we're going to do is we're going to enlarge the global symmetric space by putting some extra spaces at infinity, okay? And we're going to have them, they're going to correspond to these parabolic subgroups, but we only want the rational parabolic subgroups. So these are, if we take the standard one, that standard block upper triangular subgroup, if we conjugate them by the rational point, so that means SLNQ, okay? And this already is familiar from the case of SL2. If you take the upper half plane and you add these proper parabolic subgroups correspond to the Borel subgroup and conjugates of that. And we know that when we want to compactify the modular curve, we only add the rational points at infinity to the upper half plane. In other words, we add P1 of Q. We don't add P1 of R. The reason we do that is that if we add P1 of R, we're going to get something very bizarre when we try to divide by the action of gamma. Okay? The rational points at infinity for the upper half plane are in one orbit of SL2Z, but there are uncountably many orbits in the real points of the projective space at infinity for the upper half plane. And we can't put a topology on those points so that we get something nice after we mod out by gamma. All right. Now the structure of what these spaces are, XP, that depends on which compactification that we're doing. So if we're doing the Borel-Serre, it's going to be one thing. If we're doing reductive Borel-Serre, it's going to be something else. But the yoga is the spaces are indexed by rational parabolic subgroups. And what we take for those spaces is actually going to be built out of the internal structure of those subgroups. And what we do with them depends on what we're trying to accomplish, what space we're trying to make. There's one thing that I'm going to ignore, and that is that we don't, we're going to be taking a disjoint union of D with these other spaces, and we have to put a topology on that because we have to have a topology on the quotient. And I'm not going to really say anything about how that works. You will hear about that tomorrow, I believe, for SL2 at least. And you know what it looks like for SL2 in the cusp case. There's, in fact, what's called the Satake topology, what the neighborhoods of the points at infinity in the upper half plane look like. Okay, so I won't say more about that, just that this is the general idea. Indexed by rational parabolic subgroups, what you take depends on the compactification you're trying to make, okay? And furthermore, I want to say that you're going to be taking these spaces for these different parabolic subgroups, and there's going to be relations between the spaces at infinity. If you have a refinement of the block structure, then you want to have a relation between the spaces that you add at infinity. It's really about the topology here. If pi prime refines pi, then that space at infinity should be in the closure of the other one. Okay, so that's sort of some obvious compatibility. Those subgroups are clearly related as subgroups of SLN or G. So we want some kind of relation between the spaces. Okay, now inside the parabolic subgroup, we have these two special subgroups, which I'm calling M pi and I'm calling U pi. So U pi is a unipotent group. It's the unipotent radical of P pi. So what does it look like? It has identity matrices going down the diagonal of the same block shapes as determined by pi. So it's just take the diagonal part of P and replace it by the identity matrix. And then you allow arbitrary entries upstairs above those, okay? So in the case where P is the Borel, which corresponds to pi having as many parts as possible, that's just upper triangular matrices, then you just have ones in the diagonal and you get the subgroup UN that we talked about last time. And then we have what's sometimes called the Levy factor, which is where you have the diagonal, the block matrices on the diagonal, okay? And those look like little copies of GLN. And they, their product determinant has to be 1 if we're working in SLN, but in any case, don't have to think too hard about that. Just if you want to pretend that they're SLN, little copies of SLs for lower indices, that's fine. It's not going to really change much what we do. Okay, and those are sort of the key ingredients in building these spaces XP. These are the sort of the things we have inside of our subgroups P that actually variants of these make sense for any algebraic group G. So this is the tools we can use to make compactification. That's one thing we can, so if we change the spaces at infinity, we're going to be playing with that. We can also change which pi these boundary types actually show up. And that's what happens in the Satake compactifications. We get different, we don't get all compositions. We don't get all of these subgroups P pi. We get different ones depending on what we're looking at. Okay. So let me just say in general what they look like for these examples. So in the Borel-Serre, the boundary strata that we get bundles over the locally symmetric spaces for the smaller SLs. So in the parabolic subgroup, we have these, I think you can see my mouse, we have these M's. And so if we make the symmetric spaces for them, we get a product of lower copies of these SLN symmetric spaces. And we have a fiber bundle over that, and the fiber bundles come from the unipotent groups U pi. So those are called nil manifolds. If you take this unipotent group and mod out by a discrete subgroup, you get this nice collection of manifolds that are very interesting to play around with. They're a good example of manifolds for algebraic topology problem sets, as it turns out. In any case, they're different from sort of the usual beasts that you encounter, and they're fun to play with. So those are what we were seeing in the Hilbert modular case when we had the torus bundles. Those torus bundles were the tori there were the nil manifolds, and the smaller symmetric spaces were the little circles. Okay. Whoops, sorry. Okay, but in the reductive Borel-Serre, we squash away those nil manifold fibers, and the symmetric spaces survive. Oh, that's a misspelling. Sorry, they survive in infinity. Okay, and then these we use all of the types. But in the Satakes, you could think of it as starting with this reductive Borel-Serre and then squashing away some of the boundary components, collapsing them down. So let me show you a picture, kind of a fanciful picture that I learned as a graduate student of what these compactifications kind of look like for SL3. So Y gamma is 5-dimensional, okay? So 5-dimensional space. And we have 3 block types. We have 3 compositions of 3. We have 1, 2, 2, 1, and 1, 1, 1. Okay, and so we're going to get 3 different kinds of strata at infinity in the Borel-Serre, and then 3 different kinds in the reductive Borel-Serre. So what do these strata look like? Well, in this case, the lower rank symmetric spaces are just those for SL2. So those are modular curves. So those we understand pretty well. They're just topological surfaces. And now in the Borel-Serre, we get bundles over them. We get in this one over here, you see we have here, whoops, what am I doing? It's not what I want to do. My mouse betrayed me. So there we have we have a modular curve, and we have a torus bundle over it. That's what the little torus is supposed to be. It's like you have one of those over every point there. And I've drawn it that way because if you look at the unipotent radical for that parabolic subgroup, it has stars exactly on the top row. And so that really is like that little torus coming from, if the matrix looks like one star star, and then the rest is the identity matrix in the bottom corner. So that torus is really coming from those two entries up there. So it's horizontal, okay? And then on the other side, you have this other block type that's maximal, which is 2, 1. And then the unipotent radical, U21, now it's the horizontal, there are horizontal stars. If you go back and look at these, this matrix U pi over here. And then over the Borel corresponds to this point that gets glued in to the locally symmetric space is just a point in that case. It gets glued in there to the two at the cusp, and I've drawn them like cusps there. And then you have a three-dimensional thing, which is totally doesn't look anything like what I've drawn there. But I'm just trying to show you that there's those two tori sort of fit inside there in a nice way. So this U111 is just the upper triangular matrices with 1 on the diagonal. And that space that the little gray box is supposed to be that subgroup with real entries divided by the same thing with integral entries. So it's a very interesting three-manifold that is very fun to play with explicitly if you haven't ever thought about it before. And then you see it's a manifold with boundary in that we have four-dimensional boundary component there, and they're intersecting in this three-dimensional sub thing. But they intersect nicely, and topologically, we just have something that looks like a four-dimensional manifold glued out on the outside. In the reductive Borel-Serre, what happens is that torus bundle and that nil manifold bundle, actually that three-dimensional three-manifold that I was talking about is sometimes called the Heisenberg manifold. Anyway, it gets squashed away, and we just are left with a point. So now this is a singular. So you can't really appreciate how singular the space is because Y gamma looks like it might be three-dimensional. But remember that Y gamma is five-dimensional. So that's quite the local topology of that space is quite complicated now. So this reductive Borel-Serre, the right-hand thing, is the same as what we would call the maximal Satake. There are two other Satake compactifications that you can make. And they come from this reductive Borel-Serre by doing further squashing. You take either one of those two types and you squash them away. And you're left with something that's quite singular now. And one final thing to say is that I've only drawn one copy of each of these sort of boundary strata types. And when you take an arithmetic group, gamma, and you divide by that, you typically have many copies of these all glued together in an intricate way, okay? So I've just sort of schematically wanted to show you what happens. So I've only drawn a small piece of it.
So,
okay?
Paul, so Y21 is a four-manifold, and it has multiple boundary components. One of them is Y111, which is a three-manifold.
Right, and there's going to be more things. So if Y211 is like a modular curve with a torus bundle over it.
Okay.
And then, but at those points that are missing from the modular curve, so now that's a four-dimensional thing. And those points that are missing, we're going to glue in something three-dimensional.
Yeah.
So now that becomes itself it looks like a bundle over the Borel-Serre, over a compactification of, the Borel-Serre of that modular curve.
And the two Y12 and Y21 are being glued together at this boundary, which is a three-manifold. So the whole thing now becomes the whole boundary is still a four-manifold as it should be.
It's right. It's like a four-manifold where along parts of it, you have a distinguished three-dimensional things.
Okay.
Where it's glued together.
Thanks.
But you should be telling me because you're the expert.
No.
Yeah, so these are really, really beautiful spaces. Really fun to try to think about different. So, for if you like thinking about things like this, as an exercise, a very good exercise, like an exercise like go lift the weight machine instead of lifting the weights, try for SP4. try to think about what these spaces look like for SP4. I haven't really told you nearly enough to, but if you start going and looking in the literature and thinking about it, you'll be able to produce something exciting from that. Okay, and then one of the reasons I mentioned this is that when we are looking at our examples later on, these Satake compactification, this minimal Satake compactification is actually relevant for us. So the natural thing to do when we do this explicit reduction theory ends up involving this very singular space. Okay, I just want to say very quickly about more about the Eisenstein cohomology. So in some sense, the boundary of the Borel-Serre is what's producing that Eisenstein part in the for the modular curve. And that's true in general. And so it's a general theory of Harder. We certainly can't do justice to it here. But let me just mention that if you take the Borel-Serre and we define the boundary, then of course we have the cohomology of the Borel-Serre is the same as the cohomology of the thing without the boundary. They're homotopy equivalent. And if you take the inclusion of the boundary into the compactified thing, you get a restriction map in cohomology. Okay, you get a restriction map from the cohomology of the Borel-Serre to the cohomology of the boundary. And we call the interior cohomology the part that's the kernel of this map. So the stuff that restricts trivially to the boundary. And the Eisenstein cohomology is the subspace that restricts non-trivially to the boundary. So the interior cohomology that's where the Cuspidal cohomology lives in that range. So that's the part that somehow is the interesting part of the cohomology. It's not the same as the Cusp cohomology in general. There can be more stuff there, but it at least that's not the part that's coming from the boundary in some sense, okay? And this sort of the Einstein cohomology is a subspace of the cohomology of the Borel-Serre that comes from the thing on the right-hand side of that map R. And so Harder developed a sort of a general theory for how to try to build the subspace sitting inside the cohomology of the Borel-Serre from the cohomology of the boundary. So to do that, you have to make a section to this map R. You have to start with some cohomology on the boundary and somehow go backwards against the map R to get something inside the cohomology of the whole thing. And the technique of doing that involves using Eisenstein series, general Eisenstein series. It's a very beautiful theory. It's not completely understood by any means. There are lots of examples that are well understood. The case for GL2 is pretty well understood. But already for SL4, if I were to say take gamma to be gamma naught of n and take trivial coefficients, tell me what this subspace is for any n, we don't know how to do that. It's very complicated. So the construction going backwards again, going in the direction of the map R is of course easy. That's just a standard map in cohomology from restriction. But if you go the other way, you have to do some work and try to make a section. And we don't, in that process, that's in fact, when I was on the very first slide, when I was talking about special values of L functions, I had this in mind. Constructing the section to this map to try to get a nice subspace of H star corresponding to the boundary often involves looking at certain L functions, whether or not they vanish. So it's very subtle business. But I just want to sort of point out that there is something like what you see for the modular curve with the cusp forms in the Eisenstein series, but it's substantially more complicated and substantially less well understood. Okay. Now, finally, in the last, I don't have much time, but I'll try to get through the slides that I have today for explicit reduction theory. Okay, so why do we want this? Well, we want to actually compute cohomology by doing some combinatorial topology, like simplicial complexes, CW complexes, etc., and the associated chain complexes. And so we have spaces, Y gamma, and if we have some way of producing this structure on Y gamma, then we can use it to compute cohomology, okay? And at least for some gamma, we can do this. We have a long history of this explicit reduction theory. Goes back to Voronoi and Kocher, Lon, Soulé, and Ash, and many other people have played a role. I just can't write all names. There's a lot of work with this. And the main point is that it's not going to work for every symmetric space. We can't do this just for any group G, but we can do this for the symmetric spaces that have what's called a linear model. And in practice, this means that it has a model in terms of quadratic forms or something like that. Just like we did with the compactifications, we want to somehow be able to work with all arithmetic groups simultaneously for a given algebraic group G. So that means we don't try to focus on finding an explicit complex for one particular Y gamma. We try to find some structure on D that's gamma equivariant, and we work with that. Okay, but there are some complications. So one of the complications is that Y gamma is not compact, okay? It's not the biggest deal, but it does make some things inconvenient from this point of view. So there's sort of two different ways you can try to deal with this. So we can try to get a cell structure not on Y gamma, but on some compactification of Y gamma. And I'm not saying which one, I'm just saying some appropriate compactification. So if you can do that, and if you have, if you have that, then you can, at least under good circumstances, you can work with the relative homology of the compactification modulo its boundary, okay? You'll definitely be hearing more about this from, well, from Philippe and also from Peter and Jenny as well, I'm sure. That's one way to deal with this non-compactness problem. Compactify and work relative to the boundary. Another way to deal with it is to try to construct something that is compact that sits inside, and it's called a spine. So this is a deformation retract of the thing that has the sort of the smallest possible dimension, and that's the dimension of the VCD. And this is just another way to do it. It has, both of these have their advantages and disadvantages, I would say. But in any case, there are sort of two different themes here. So if you think about the modular curve, you see sort of both of these in action. You can either work with the homology of the modular curve mod its boundary, or you can take those punctures and just deformation retract that thing onto a graph and work with that, okay? The other complication is that the groups typically have torsion in them. Remember I said in the last lecture that we have this isomorphism between the group cohomology and the cohomology of a space, but it's not true if you're working with integral coefficients and the group has torsion. So there are various ways to deal with this from this combinatorial point of view. So first of all, you could just accept that you have torsion and try to make a cell structure where this group gamma acts freely, so that the no cells are stabilized by anything other than the identity, okay? If you can make a complex like that, then you can just work with that complex. You don't have to worry about it. You're fine. On the other hand, another way to do that is to modify the coefficients and accept that, okay, you have torsion, but the torsion subgroups are finite. We have finite stabilizers on some complex, and we just deal with that. We accept that, and we use coefficient systems, say by taking rational coefficients or inverting some few small primes, and just accept that we're going to have this, and then we can do what we want with the cell structures on which we have non-free actions. So Philippe is going to talk about that for sure. Various ways to do it. It sounds scary, some of the things that I've written there, but it's not so bad, as we'll see. And in fact, usually what happens in real life is that if you have a nice way to do reduction theory to make a cell complex, typically you wind up with something where gamma acts with finite stabilizers. It's just a fact of life. If you have that, you can make something on which gamma acts freely by just doing barycentric subdivision and adding more cells. But when you do barycentric subdivision, you add a lot of cells. And so that tends to make computations much more difficult to do if you're trying to do explicitly. I mean, it can mean that a computation that you can do on a reasonable computer versus a computation that you can't do on any computer. So we tend to prefer the latter approach, okay? That does mean we have to give up working with integral coefficients completely. We can, if we throw away some small primes, we can still do the work, but we can't get the full integral cohomology, which is unfortunate. It'd be very nice if there were some way to make that work for all coefficients z, but it just seems to be unknown how to make that work. It's just too complicated. And then that's when these fancy words that I'm using in the parentheses really start to play a role. That's where the complication comes. Okay, so here's an example, classical example, SL2Z. So this is the upper half plane, and the gray triangles, ideal triangles that you see are, we take the triangle with vertices at 0, 1, and infinity, and we act on it by SL2Z, and we get this beautiful tessellation of the upper half plane, sometimes called the Fourier tessellation, but I'll call it the Fourier-Voronoi tessellation in honor of Voronoi too. So you've learned last week about Voronoi's theory for perfect forms and its relation to lattice packings and stuff like that. These gray triangles are the images of the Voronoi cones in Sim2 plus R, which means the positive definite quadratic forms and with real coefficients in 2 variables. That's the notation I'll be using for that. Okay. So I know, because I actually watched some of the lectures last week, that you've definitely seen that. So I don't have to, at least at the moment, define much more about it. But there it is. We have this beautiful tessellation of the upper half plane by ideal triangles, and it's constructed using Voronoi reduction theory. If we take H star to be the upper half plane with P1 of Q, so the rational points in the real axis and also the point at infinity, and we give it the right topology, then when we take the quotient, we're going to get a CW complex structure, okay? So those points at infinity, we don't take all the points along the real axis, but we only take the ones corresponding to the rational points and the one at infinity. And then we're actually going to have a nice structure on the quotient, at least if gamma is torsion free, then we're going to actually have a triangulation of a compact surface, okay? The blue subset that I've drawn there is the deformation retract. So this is this famous SL2 tree. It's also known as the well-rounded retract. It generalizes to other settings. It's compact, and it's a deformation retract of H2, and the deformation retraction is SL2Z equivariance. And you can imagine how to do it. You just start taking those gray triangles and collapsing them down until you get to the blue thing, okay? So now the blue thing is compact mod gamma, and that is in fact our, that's exactly the graph that this thing deformation retracts onto. And let me just point out that these triangles, if you've studied modular forms, and you've seen plenty of pictures of triangles in the upper half plane, but these are not fundamental domain for the action of SL2Z. You know from the modular forms that actually the fundamental domain, how do you make it? Well, what you would do is take one of these upper blue arcs and then draw vertical edges going up, straight up. And then that triangle, which is not an ideal triangle anymore, is a fundamental domain for the action of SL2Z. So even in this simplest case, we have the reduction theory gives us something where there's a finite stabilizer. There's a stabilizer in SL2Z that or PSL2Z, since the center acts trivially, that rotates around those, take one of those points and rotates that tree around those points. And there's even another subgroup too, corresponding to flipping the gray edges. So there's definitely some torsion in the group, and we don't have a fundamental domain, but we have something very close to one, okay? For SLN, we can do the same kind of thing. So this is, again, this was discussed last week. You take the vector space of real quadratic forms and you take the positive definite cone, okay? And then at infinity to that cone, we adjoin some boundary components. And these are not going to be, we don't take the closure of C inside V. We adjoin the rational semi-definite quadratic forms. So these are the ones that they're rational. Of course, their kernels are rational subspaces of Rn. So they have a kernel, they're not necessarily just zero. But otherwise, they're non-negative. So we adjoin those at infinity. An example of that is the space of rank 1 quadratic, these rank 1 quadratic forms that I know Renaud talked about last week. You've definitely seen that. So those are some points there. Then this cone gives you a model for the symmetric space for SLN cubed. It's just that it's not the right dimension. If we mod out by homotheties, then we actually recover the global symmetric space for SLN R over SLN. Okay, so it's one dimension more than our symmetric space D, but that dimension is just coming from the fact that it's a cone. You just divide by that and you get D. Or if you like, you could also take the determinant 1 quadratic forms sitting inside that cone. That would also give you a model, but I think it's nicer to divide by homotheties. And if you take D with those boundary components, you will get a certain symptotic compactification. You get one of those, you get one of the minimal ones. And when we mod out, so the reduction theory comes from, I know I'm a little bit late, but let me just get through these last 2 slides, sorry. The Voronoi polyhedron, we take the convex hull of these rank 1 quadratic forms, psi, and then the perfect cones are the cones generated by the maximal faces of that. If you take those cones and their faces, that gives you a decomposition of this cone in the big cone into smaller polyhedral cones. And modulo homotheties, they give you cells in D with these boundary components adjoined. Finally, by modding out, after we mod out by a finite index subgroup, we get a CW structure on the symptotic compactification, and we can use it to do cohomology computations. In fact, we can take the boundary, we can work modulo the boundary and take homology, and we'll be getting the cohomology. And that's part of what the Borel-Serre duality discussion that will be tomorrow. And just one more quick slide, just to say that the same thing works at least as written for imaginary quadratic number fields. Here I just took the example of z adjoint square root of -1. So I replaced the vector space of symmetric forms over R with the hermitian forms over the complex numbers. It's a real vector space. And then I have a positive definite cone. I join boundary components corresponding to the semi-definite rational hermitian forms. And these again include these rank 1 guys, which are gotten by taking integral vectors over this ring, z adjoint square root of -1, and then making this product. But now I have to take the complex conjugate as well as the transpose to make a rank 1 form. The symmetric space becomes the symmetric space in this case, SLNC divided by SUN. We make the Voronoi polyhedron in exactly the same way. You can think about it in terms of perfect forms. So you take the cones on the faces of the convex hull of these points psi, and you get a polyhedron. And then the cones on the faces of that polyhedron give you a cell decomposition, which again gives you a CW structure on the quotient. You don't get the Borel-Serre this way for any of these examples because you don't have enough stuff at infinity that you've added to produce the Borel-Serre. You get something quite singular, but it's still good enough for what we want to do with it. And of course, you can use other imaginary quadratic fields too. So that's the last slide for today. The next lecture, I'll be continuing talking about this explicit theory and talk about what you do for general number field. That's it.
Thank you, Paul. Sorry for holding you back with all the questions in the middle.
No, you didn't hold me back, not at all.
I think Graham had a question.
Okay.
Yeah, well, I interjected. I'm not sure exactly what it says. You were talking about the cell stabilizers in the complex. And did you say that you can barycentrically subdivide so that the stabilizer groups disappear? My understanding is you can move stabilizer groups around, but you can't produce. I didn't think you could produce a free action of it. Maybe we might be talking about different things.
Did you hear what he said?
Yeah, I think, okay, it could be that I'm wrong about that you have to do it once. Maybe you have to do it twice.
I mean, you have to increase the, I agree with Graham. I don't think you can get a free action just by barycentrically subdividing, because you have to increase the dimension to infinity in order to get a free action of a finite group.
Okay.
But you can move you can change the stabilizer groups and push them to different dimensions and so on of cells.
Yeah, okay. You can't compute if you have if you have cohomology that's appearing in degrees outside the the range, the dimension of the space. You're not going to see that.
maybe what you meant is that you could have cells that are globally stabilized but not pointwise, and if you subdivide them enough, then you can get all cells that have a non-trivial global stabilizer to be actually pointwise stabilized.
Yes.
That I think you can achieve using barycentric subdivision.
Yes.
I agree.
Sorry about that.
Are there any other questions? Well, I have some questions for Paul, but maybe we'll do that after we thank Paul again and have everybody go home.